A new method for controlling light could strengthen future wireless communication. Scientists have developed a new optical device that allows precise control over highly stable, vortex-shaped light patterns in advance that could play an important role in next-generation wireless communication technologies. If you like my videos, subscribe my channel and press the bell icon to turn notifications on so you keep getting all the major advancements in science and technology. And don't forget to like and share this video with your friends and colleagues. The device generates and switches between two distinct forms of structured light known as skyrmions. These patterns resemble donut-shaped vortices and are remarkable for their stability. Even when disturbed, they retain their overall structure. This robustness makes them attractive candidates for encoding and transmitting information in environments where conventional signals are easily degraded by noise or interference. Stable light patterns for reliable data transmission. The research team demonstrated that their device can produce two different skyrmion configurations, one dominated by electric fields and the other by magnetic fields within freely propagating terahertz light pulses. Crucially, the system can switch between these two states on demand using a single, integrated platform. This level of control is essential for practical communication systems. To reliably encode information, a signal must not only be stable but also reproducible and selectable at will. The ability to switch between distinct, well-defined light states opens the door to using light's internal structure, rather than just its intensity or frequency as a carrier of information. The work was reported in Optica, where the researchers described the first experimental demonstration of actively switchable skyrmions in free space terahertz radiation. The role of metasurfaces. At the heart of the system is a nonlinear metasurface, an ultra-thin material patterned with nanoscale metallic structures. Unlike traditional optical components, metasurfaces can manipulate light with exceptional precision, reshaping its phase, polarization, and spatial structure. When ultra-fast near-infrared laser pulses strike the metasurface, it converts them into carefully tailored terahertz light pulses. By adjusting the polarization pattern of the incoming laser, the researchers can determine which skyrmion mode is produced. One polarization configuration generates an electric mode skyrmion, while another produces a magnetic mode skyrmion. This mechanism is conceptually simple but powerful. Changing the input light pattern directly selects the topological state of the output signal. Why terahertz light matters. Terahertz radiation lies between microwaves and infrared light on the electromagnetic spectrum, and is widely viewed as a key resource for future communication and sensing technology. Terahertz waves can carry large amounts of data, but controlling them precisely, especially their spatial structure, remains a major challenge. One particularly promising structure is the toroidal vortex, in which the electromagnetic field forms a closed, ring-like loop. Such vortices provide additional degrees of freedom for encoding information. However, most existing systems can generate only a single vortex pattern and lack the ability to dynamically switch between different states. This new device directly addresses that limitation by enabling programmable terahertz light structures that can be actively controlled in real time. Experimental validation. To verify the performance of their system, the researchers used an ultra-fast terahertz measurement setup capable of tracking the light pulse as it propagated through space. By sampling the electromagnetic field at many positions and time delays, they reconstructed the full evolution of each pulse. These measurements clearly distinguished between the electric and magnetic skyrmion modes and confirmed that switching between them was both reliable and precise. Fidelity analysis showed high purity for each mode, indicating that the device produces clean, well-defined light states with minimal cross-contamination. Looking ahead. Future work will focus on improving the system's efficiency, long-term stability, and compactness, all of which are essential for real-world communication applications. The researchers also aim to extend the approach beyond two switchable states, enabling multiple controllable skyrmion configurations. Such multi-state control would allow more complex and flexible information encoding schemes, potentially leading to wireless systems that are faster, more resilient, and better suited to the demands of next-generation networks. In essence, this research demonstrates that the topology of light itself can be engineered, controlled, and used as a practical resource, a concept that may significantly reshape how information is transmitted in